Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, and on behalf of those folks and our other co-organizers, Wisconsin Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you two people, Keith Bechtol and Ellen Bechtol. Keith is in the Department of Physics, and Ellen works for the Large Synoptic Survey Telescope and also for IceCUBE. Ellen was born in Charlottesville, Virginia, and went to high school at Arlington, Virginia at Washington Lee High School. She went to undergrad at the College of William and Mary in Williamsburg, Virginia, and studied American Studies, and then got her master's degree at John F. Kennedy University in Berkeley, California, in museum studies. Keith was born in Alexandria, Virginia, and went to Thomas Jefferson High School there. He also went to the College of William and Mary and studied physics, then went to Stanford and got his master's and PhD in physics there. He did postdocs at the University of Chicago and here at UW-Madison. Then he moved to Tucson, Arizona to be a staff scientist with the Large Synoptic Survey Telescope. And then in August, moved back to UW-Madison to be on the faculty here in physics. Tonight, they get to talk to us about the big picture, science and public outreach with Astronomical Surveys. Keith is going to talk first, so why don't I welcome Keith up to the lectern. Please join me in welcoming Keith to Wednesday Night at the Lab.
All right, thanks a lot for having both of us here. So this will be a presentation in two parts. I'll start by giving a little bit of an introduction to astronomical surveys, and then I'll hand it over to Ellen, and she'll tell you about all the education public outreach opportunities. So this is a picture of the Large Synoptic Survey Telescope that's under construction in Chile. So throughout this talk, I'll provide some examples and point to LSST as an example of one of these survey instruments. But I want to actually start off by describing what are astronomical surveys. So it's a really exciting time to be giving this talk and talking about astrophysics, because you may have heard in the news last week that we were able to acquire the first image of the event horizon of a black hole. And this is a tremendous scientific breakthrough. And it's also an example of how you can use astronomical facilities to study a particular object in detail. So on the right here is a radio image of the black hole with the Event Horizon Telescope, and on the left is an optical image taken with the Hubble Space Telescope. And these are extremely specialized observations to achieve this high angular resolution. The instruments that take this are really designed specifically for this purpose. Now, this is different from what we try to do in survey astronomy. In a survey astronomy, we try to map as much of the sky as possible. And it turns out that you want to use different types of instruments for doing that type of research. The reason is that even if you use an extremely powerful and precise instrument like the Hubble Space Telescope, you're only able to image a small fraction of the sky at a time. So the image here is taken by Hubble. It's one of the most famous images that Hubble has taken, where they looked at just what appeared to be sort of a blank spot in the sky, and they see thousands of galaxies, right? This image here, you can see the inset next to the full moon, and you see that it's a really small fraction of the sky. It would take something like 10 million photos of the size to cover the full sky. So Hubble is an extremely powerful instrument, but it's not the instrument that you would use if you want to map as much of the universe as possible. We think that there's something like 2 trillion galaxies in the whole observable universe, and right now we've seen just a fraction of them. So the idea of an astronomical survey is that you try to cover as much of the sky as possible. You go very wide, you try to image as quickly as possible so you can scan the sky, and you try to go as deep as possible so you see as many astronomical objects as possible. So this is showing the field of view of the dark energy camera, which is one of the instruments that I use. And you can see that it's actually much larger than the full moon, right? This is a field of view that's substantially larger and actually gives us a reasonable chance of mapping large portions of the sky. So we've been going on this enterprise now for several years. And this is showing a representative patch of sky that corresponds to half of one of the individual CCDs on the previous image. If you look closely here, you can see that the whole focal plane of the dark energy camera actually consists of 62 individual CCDs and arranged in a mosaic. So if we could just zoom in on one half of one of those CCD chips, every single one of the objects encircled in green represents an individual star or galaxy that's been detected in the images. And so by mapping approximately 1/8 of the sky over the first 300 nights or so of operations of the dark energy camera, we've now cataloged something like 400 million individual stars and galaxies. And these are going out to objects that are 10 million times fainter than we can see with the human eye, galaxies where we're seeing light that was emitted 10 billion years ago. This is another glimpse of what survey astronomy can do. This is a composite image assembled with data from the Gaia spacecraft, which was launched by the European Space Agency. So in this image, you see the collective light of the brightest 2 billion stars that are visible from Earth. Right? They're mapping the entire sky and looking at the very brightest stars. And so you can create beautiful images, not just of a portion of the sky, but really getting a synoptic view of the entire universe as from our perspective here on Earth. One of the really amazing things about taking these images is that we're actually sensitive to being able to see objects and to do science on a huge range of different size scales. So this is just one image with the dark energy camera, and I like this image because you can see physical phenomena on just a huge range. So let's start from the most distant objects and work our way back in. So it's probably a little bit difficult to see for you guys in the audience, but if you could look closely at this image, you would see that the smallest smudges of light are distant galaxies that are billions of light years away, and these comprise most of the objects in this image. Now these larger extended spiral galaxies that you can see in the foreground, there's 2 of them. These are nearby galaxies. These are maybe a few million light years away. They're close enough that we can actually see the structure of the galaxy easily. Now this bright blue point of light in the lower left, that's one of the stars in our own Milky Way. So that's something that's of order light years away, maybe hundreds of light years away, so much closer. And then it's a little bit difficult to see, but in the very top right-hand corner, you can see an object that there's two neighboring points of light. One is red and one is green. Okay, we interpret that as an asteroid that was moving through this field of view, and as we were taking pictures of this part of the sky in different color filters, it showed up in one color filter, on one image, and then showed up in another color image a bit later. And so this is an object that's in our own solar system that's maybe light minutes or light hours away. Right? So in this single image, you see just this enormous range of astronomical phenomena, an enormous range of science that you can do with one data set. So why astronomical surveys? Why are we so interested in this? So I'm a physicist, and so the way that I like to think about this is that our universe is just one realization of a statistical process that's governed by the rules of nature. And so we kind of get one opportunity to see how these laws of nature have built up all the galaxies in the universe that we can see. As a physicist, we aim to discover what these rules are. And the interesting thing is that some of the patterns, some of the physical laws that we would like to discover, they're effects that only appear when we look at the universe on the very largest scales. They're not something that you can see by looking at a single star or a single galaxy. And to give a sense of what I mean, I want to show an image of the cosmic microwave background. So this is not optical light, but looking at a part of the radio or the microwave spectrum. This is taken with the Planck spacecraft. And it's showing the color scale here is representing density fluctuations in the very early universe. This was light that was emitted about 400,000 years after the Big Bang. And the density contrast between the least dense and the most dense regions of the universe at that time was about 1 part in 100,000. That's about the same level of fluctuations in density as when you're speaking, the density of air that's created by your voice. Okay? So very, very minute perturbations. Out of that grew all of the galaxies that we have in the universe today. And when we look at an image like this, the way that we characterize it is statistically, right? We look at the pattern of the denser spots and underdense spots, and this reminds us that what we're actually seeing is literally quantum fluctuations that have been blown up to the scale of the universe. Okay. Perhaps the most amazing thing about all of this is that at least on one planet, there's intelligent life that's looking out there and trying to understand what it means and our place in it. And the remarkable thing is, right, that the universe seems to be governed by mathematical laws, that we actually have some chance of understanding it and understanding what our context is in this. One of the really surprising things that we've learned over the past couple decades is that even with our powerful optical telescopes, we're only seeing a really small fraction of all the matter and energy that's out there in the universe. It turns out that something like 95% of all the mass and energy in the universe exists in forms that are invisible to us. We give these names, these phenomena names like dark energy, dark matter, neutrinos. We know that they're distinct physical processes, but in a large sense, these names are placeholders for physics that we don't yet fully understand. And what's kind of perplexing and makes us so curious about these is that we can't touch them, we can't feel them, they're invisible, and yet they determine the fate of the universe, right? So we would like to understand them. Let's focus on one of these just to go a bit deeper. So one of the topics that I study is dark energy. This seems like it's some form of energy that permeates all of space and is constant in time. It has the effect of driving galaxies apart. So over time, the spaces between galaxies are growing at an accelerating rate. And the easiest way for us to explain that is that there is some form of energy density out there that's driving them apart. Now, you might think, okay, there's all this energy out there. Why can't we sense this? Why can't we see this? So it turns out that if you use Einstein's famous formula relating energy to mass, if you were to take this dark energy and ask, what is that corresponding density in terms of matter particles? It turns out that the density is about 4 protons per cubic meter. And this is an energy density that's everywhere. It's in this room, it's in the space between stars, it's in the space between galaxies. It's what's driving the overall evolution of the universe right now. It's the largest component. Now, if you compare that extremely small density, 4 protons per cubic meter, to, say, the density of interstellar space, right? Interstellar space, we think of it as a vacuum, but it's something like 1 million protons per cubic meter. The air in this room is something like 10 to the 27. That's a 1 with 27 zeros after it, protons per cubic meter. And something like water, like what our body is made of, is 10 to the 30. So in terms of what we can sense here on the Earth, it's extremely small, but the universe is really big. And so when you average over the entire universe, this dark energy is actually by far the dominant component. And that's pretty surprising. So you might wonder, how can you study something like this that's invisible, that you can't touch it, you can't feel it? And the answer is that we have to look at statistical properties of the universe. And this is where the astronomical surveys come in. So this is a map of galaxies. It's showing one narrow slice in a large 3-dimensional map of galaxies. And each of the yellow points here represents the location of one galaxy. As you go further out from the center of the image, you're looking at galaxies that are further and further away. And you may notice, if you look at this image for a moment, that the galaxies aren't randomly distributed. They're actually sort of clustered into filaments and kind of like bubbles and clusters and so forth, right? And then there's large gaps between them. And this structure here is actually exactly what you would predict from doing cosmological simulations and understanding how gravity operates on matter over billions of years. So we can do precise numerical simulations, and we can compare the distribution of galaxies that we would predict to that which we observe. And again, this pattern of structure, these filaments and these elongated structures, it's something that's only visible on the scale of hundreds of millions of light years, or at least tens of millions of light years. It's not something that you could detect by looking at a single galaxy. It's something that we need a large map of the universe to be able to see. Another example of one of the tools that we use to study dark energy are supernovae. Now, these supernovae, they're extremely luminous stellar explosions that we can see over great distances in the universe. And they're excellent tools for studying dark energy. The challenge is that these supernovae are extremely rare and unpredictable. In a given galaxy, you may have one supernovae per 1,000 years, right? But in order to study these supernovae in detail, we like to acquire additional observations with other telescopes. And so how do you plan these observations when you don't know when the supernovae will occur? The solution is that you just look at as many galaxies as possible. If you look at thousands and thousands of galaxies, then in the course of a human lifetime, in the course of an experiment, right, you don't have to wait forever, you'll see some of these supernovae. And the people who pioneered this called the supernova on demand, because they didn't know where the supernova would occur, but they knew if they looked at thousands of supernova that they wouldn't have to wait for too long. So once you have one supernova, that's not enough, right? You actually want hundreds or thousands or even hundreds of thousands of supernova to actually see the cosmic expansion history. And so this is a plot from one of our recent papers. And you don't need to understand the details. The point of this is just that by collecting the data from many, many, many supernovae, you're able to distinguish between different models of dark energy. But you couldn't do that with only a single supernova. You need this ensemble of measurements in order to make the inference. Another technique that we use is called weak gravitational lensing. This is a way of measuring the total mass distribution in the universe. And so this image is showing the mass distribution over about 1/20th of the full sky. The regions in red and blue are showing regions that are either more dense or less dense. And again, this pattern of seeing regions that are more dense or less dense, it's only a pattern that you could see by making this large map of the universe. If you only looked at a single galaxy, you wouldn't even be able to measure this weak gravitational lensing effect. It's an example of something that's entirely a statistical measurement. One more example that's a bit closer to home. So far we were talking about the whole distribution of galaxies throughout the universe. What if we just talk about our own Milky Way, our own Milky Way galaxy with its 100 billion stars or so? Well, if you actually look at those stars in the Milky Way, you see that they are also not randomly distributed, but they actually have many structures around the Milky Way. And in particular, some of the most dramatic structures are these so-called stellar streams. These are like rivers of stars in the sky where another galaxy has come too close to the Milky Way and it's been pulled apart by the gravitational attraction of our own galaxy. When it gets pulled apart, it forms these elongated streams of stars. And again, this is something that you couldn't see if you only looked at individual stars. But we have maps of something like 1/8 of the sky, very detailed digital maps. And so we can measure the distances of different stars, and we start seeing these structures. So on the left-hand panel here, this is showing a map of the stellar density. And it's a movie that's stepping out in distance. It's scanning in distance. And at particular slices in distance, you may see these faint black streaks that are crossing the image. These are the so-called stellar streams, right? They're these regions where the stars are all moving coherently and telling us something about how our own galaxy formed. This is something that you wouldn't be able to access except by making these large maps of the sky. So let's talk about how we do this. This will transition into a bit of the technology of how this is possible. So over the past couple decades, there's been a progression in our ability to map the sky faster and deeper and wider. And so one of the landmark players in this game was the Sloan Digital Sky Survey, which started in the year 2000 and is still going today. The University of Wisconsin is a major player in the Sloan Digital Sky Survey. This was an incredible new instrument. It was using a relatively modest telescope, only 2.5 meters across. I say only, but that's actually fairly modest in the landscape of professional astronomy. But it is arguably the most productive scientific instrument in astronomy in all of its history. What it did is that it created the first digitized maps of the night sky, and it made all of its data public so that thousands of scientists could all analyze this data. When you go to an astronomy colloquium and someone asks, hey, who here has used SDSS data, the Sloan data? Basically, everyone in the audience will raise their hand, right? It changed the landscape of astronomy, and things would never be the same after SDSS. Now, the project that I work on now is called the Dark Energy Survey, or DES. That started in 2012. And that's about 10 times deeper than SDSS, so we can see galaxies and stars that are much, much fainter. And the project that we're building in Chile is called the Large Synoptic Survey Telescope, and that'll start running in about 2023 or so and run for about a decade. LSST, as it's known, will image stars and galaxies about 100 times fainter than those that were detectable by SDSS. And so you can see that there's been this step forward in technology that's allowed us to map the sky with ever more precision. Now, the big difference between these different surveys is their amount of light collecting power. So the word that we use for this is étendue, and you can think about it as basically how many photons from the night sky that you're able to collect with your telescope. The étendue is the product of the field of view, basically how wide on the sky you can image at once, the effective aperture, so the size of your mirror, and your operating efficiency. And this plot here is showing a number of different surveys. The vertical axis is a log scale. And so you can see that LSST is something like a factor of 10 more in its light collecting power than any previous instrument. Okay? So how is this possible? What it required is actually over 2 decades of planning leading up to the moment that we have today. LSST is really an entirely new kind of telescope that's been optimized specifically for surveys. The first discussion of LSST you can trace back to around 1998 when scientists realized that there was this optical design that would allow them to achieve this very large field of view. In the year 2010, LSST was selected by the whole astronomical community as the highest priority project of the next decade. And then the formal construction of LSST started in the year 2014. It's a joint project between the National Science Foundation, the Department of Energy, and our international partners. And that's a theme, right? These projects are enormous. LSST is something like a $700 million project. But what it will do is create a data set for literally thousands of scientists and even thousands more educational opportunities for students and anyone who's interested in astronomy. So what made this possible was a confluence of enabling technologies. It really took all 3 of these to make the LSST design feasible. What we needed are extremely large mirrors, so in particular 8-meter class mirrors that are made at the University of Arizona. It took a mosaic of high quantum efficiency CCDs that are optimized for near-infrared sensitivity, so we can see the very most distant galaxies. And importantly, it took exponentially increasing computing power. Again, the vertical axis on this plot is a log scale, and each of the different types of symbols is representing the growth in these different aspects of the technology. And you'll see, for example, this computing power, this is growing with Moore's law, right? The number of transistors that we can pack is growing exponentially with time. So let's step through some of these ingredients. The first main ingredient is having this enormous field of view. So you can see represented here the field of view of several different surveys. LSST is in the lower center for reference, and you can see the full moon there in the lower left-hand corner. The next ingredient that you need is a very large aperture. So this was a picture taken of the glass that's used for the mirror of LSST. And you see all the people who were there on this day to give a sense for just how large this mirror is. This is before it gets silvered with its reflective coating. But this mirror is 8.4 meters across. It's about the size of this room. Okay? An enormous amount of light collecting power. The next key ingredient is a camera. The LSST camera is about the size of a car. It's the largest, most powerful camera ever built in astronomy. To give a sense of the key numbers of the LSST camera, it has 3.2 gigapixels, 3.2 billion pixels. If you were to take a single image with LSST and project it at its intrinsic resolution using high definition TVs, it would take the area of about half a basketball court. Okay? That is a huge amount of data, right? And we take one of these images every 15 seconds for 10 years. That's the goal. This is an image of the commissioning camera showing the array of 9 of the CCD sensors. This commissioning camera we're using as a prototype to help us make sure that the different parts of LSST are functioning correctly, and it's using only one of 21 rafts that will make the full LSST camera. So you can see in the lower left-hand part of this image someone's hand to give a sense. The full LSST focal plane is the size of a manhole cover. It's all instrumented with silicon CCDs. This is an image of the lens that's on the front of that camera compared to a human for scale. Right? So you can see how enormous this is. And we're collecting something like 10 terabytes of data a night. That's enough to fill up multiple hard drives of all your laptops. We have fiber optic that's going from the cable and leads all the way to the supercomputing facility at the University of Illinois. There is a bank of computers that are capable of achieving processing speeds up to 2 petaflops. Peta is 10 to the 15, okay, operations per second. And this is one of the big challenges of data management, right? Once we have all these images, we need to analyze them. We need to extract all of the individual stars and galaxies and measure their properties. Now with SDSS shown in the lower left, we had the advantage, so to speak, that the galaxies and the stars were all kind of distinctly located on the sky. At the LSST depth shown on the right, we see so many stars and galaxies that all of their light blends together. It's a major processing challenge just to be able to distinguish the individual objects. We see that the universe is just full of light, full of galaxies. So over 10 years, LSST aims to visit every patch that's visible from Chile about 1,000 times. The idea is that it will return to each patch of the night sky about every 3 nights. And so by collecting these thousands of images over 10 years, we'll actually not only be able to get like one very, very deep image, we'll actually be able to see everything that's moving and changing over that 10-year period. You can think of it as a 10-year color movie of about 40 billion stars and galaxies, and all the solar system objects as well. Here are some of the LSST key numbers, just to give a sense of the magnitude of what we're talking about in terms of the sheer numbers. So this is shown in a graphical representation. But if you just were to pick out some of the key numbers from this chart, these are some of the ones that I would highlight. That you have this 3.2 billion pixel image every 15 seconds, 365 nights a year for 10 years. That's about 5.5 million images. About 500 petabytes of images total collected over 10 years. There's about 10 million alerts that are distributed each night, and they're released to the world within 60 seconds of the shutter closing on the camera. There's about 20 billion stars and about 20 billion galaxies. So LSST will actually catalog something like 1% of all of the observable galaxies in our universe. There's actually a finite number of galaxies that we can see because the universe is a finite age. Like the light can only travel so far. And so with LSST, we actually start getting to an appreciable fraction of literally every galaxy that we could conceivably see. There'll be something like 30 trillion individual flux measurements. So when you have an instrument like this, it actually changes the entire way that you think about astrophysical research. And the whole landscape of professional astronomy is changing. Nowadays, we typically work in large collaborations like the one shown here. This is one of our meetings for the Dark Energy Survey, where we have hundreds of collaborators that are all working together to try to pull off a survey of this challenge, both technically and scientifically. And another big thing that we're doing is that we're making all of this data public. So instead of this model where, if you're an astronomer, you work with your particular grad students, you write your proposal, you go to the telescope, and you take the data back on one of your thumb drives. Now what you do is that you write a SQL query. You go to the database and you download the particular objects of interest. And whether you're interested in solar system objects, stars, galaxies, it's just making a different query, right? The idea is that this data set will be useful for many, many different scientific purposes. So you can think about all the science that you could do with this archival data. So some of the values that we have in survey astronomy are shown on this slide. We increasingly are moving towards open source code. We try to make as much of our data public as possible. And by doing this, we ensure scientific reproducibility. We try to make it possible for scientists to basically run the exact same algorithms, run over the exact same data, and see if they get to the same result, or maybe they'll find a better way of doing it. We emphasize collaboration, and we really emphasize equal opportunity, that by making this data public, anyone with a good idea can try to find something new. So I think this is a good point to hand it over to Ellen to talk about education and public outreach opportunities.
Hi. Okay. So I'm going to talk about survey astronomy from a slightly different perspective, that of education and public outreach. So you just heard a lot about the exciting science that can be done with survey astronomy, and I feel like there's equally exciting and numerous opportunities to engage with survey astronomy as a member of the public or in educational classrooms. So I'll use LSST as a case study, but I want to start with a little bit of context from a historical perspective. So SDSS, the Sloan Digital Sky Survey, was especially important scientifically and also from an education and outreach standpoint. And so they have a long history with bringing survey data and even some of the survey instrumentation and objects itself into the classroom. So this is a screenshot from their website, the education section of it, and you can see on the right-hand side there are three people, and the person in the middle is holding this giant plate. And that's a plug plate that is used as part of the survey to take their images. And they distribute these plates to teachers around the country, certainly when they're done using them. Another project of SDSS that really was quite widely successful was called Galaxies. And in this instance, they made a subset of the data available for the public to help them classify which types of galaxies they were seeing. There were so many galaxies, they couldn't do it all on their own, one scientist in a room alone. So they made the data publicly available. And so in the first Galaxy Zoo, there have been many additions since the original one in the year 2007. But the first one, since then, there have been more than 40 million classifications, and they were made in approximately 175 days by more than 100,000 volunteers. And they thought that it would take volunteers years to complete that data set, and it didn't take that long at all, right? So this is not meant to be representative of all of what SDSS or DES do for education outreach, but just to give you a flavor, in a sense, for what some other surveys have done. So the Dark Energy Survey, they have several projects, one of which is called Dark Bites, and this is really a blending of art and science. So they use several of their talented collaboration members, both to create artistic representations and pair them with facts and analogies about the universe. And then this is distributed online and through social media and has thousands to hundreds of thousands of views and impressions over time. Another project is called Scientist of the Week, and they also have some reflections of the observing teams. And through this work, I've noticed that they've really highlighted the diverse individuals, the diverse skill sets and backgrounds and areas of expertise that it takes to make one of these surveys work, right? It takes a lot of people around the country, around the world, with a lot of different skills to make these telescopes go day and night. They've also translated several of their education and public outreach websites into as many as 4 languages. Okay, so for LSST, Education and Public Outreach, our mission is to provide worldwide access to and context for LSST data through accessible and engaging online experiences so anyone can explore the universe and be part of the discovery process. So among ground-based astronomy projects, LSST is fairly unique in that we have substantial effort and funding during the construction phase to create education and public outreach products and materials. For a lot of the previous astronomical surveys in science in general, education and public outreach relies heavily on volunteers to donate their time and efforts and energy to make education outreach happen. For LSST, there's dedicated staff and funding in the construction phase to build up an EPO program before the survey actually is running. We have 4 main audiences: formal educators at the level of advanced middle school, high school, and Astro 101 or intro college level courses, citizen science principal investigators, content developers at science centers and planetariums, and the science-interested teens and adults, such as yourself, the general public. So during construction, EPO will build an operations website and materials in both English and Spanish, a formal education program based on online notebooks, a repository of multimedia resources, an interactive sky viewer, a cloud-based education and public outreach data center, the capability for researchers to build their own citizen science projects using LSST data, a communications and marketing plan, and a strategy for measuring success, which is what I personally work on, the evaluation component. So I'm going to step through some of these products right now. So for formal education, we're building themes, investigations around 6 themes, and these 6 themes are based heavily on the type of science that LSST will be really good at producing. So they are properties of light, properties of stars, galaxies in the Milky Way, cosmology, the solar system, and the dynamic sky. And we're building these investigations in close collaboration with educators. We have several educators on our staff, and we're also actively doing user testing and needs assessment with educators to make sure that what we're building is well aligned for their needs and their interests in the classroom. So here's an example of one of our current investigations. Everything will be on a web page, so it's easy to access. There's low tech startup cost. If you can load a website, you can load the investigation. You don't need to download any data. You don't need to download any special software or anything from a database. And this particular investigation is walking students through how telescopes collect data and then how that data is turned into astronomical imagery. And we're building an interactivity, so we will have a subset of LSST data and images available where then students can apply different filters and different amounts to make their own astronomical images and then share them out with their friends and family and their teachers. For planetariums and science centers, we are creating a library of digital multimedia assets, including a full dome sky view of that LSST alert stream that Keith mentioned not that long ago, made available every 60 seconds. I don't think our full dome sky view will be made available every 60 seconds, but it will be updated on a regular basis. We are also making media specific for Chilean audiences because the telescope is in Chile. We have a strong education and public outreach component in that country. And we're also making 3D materials. We are providing a multimedia gallery, which is actually available now, and I'll show several images from the gallery at the end of this talk, and you can see the website there, gallery.lsst.org. And these assets will be provided in formats that support emerging industry standards, so data to dome, AVM, and Immersa Dome Master. So these are all standards that the planetarium and science center community are using and will make it easier for content creators and developers at those institutions to use the imagery however they see fit. So the Sky Viewer, this is specifically targeted for members of the public, and we see this as really a self-guided educational tool. So There will be a website with some subset of the LSST dataset available, and we are hoping to curate and planning to curate objects of interest and even make some guided tours so you can explore a topic or a theme of particular interest to you, and we'll take you around the LSST night sky, and you can learn more about it and dig in to all the different aspects that you're interested in. Everything will be mobile friendly. You can use it on a tablet, on your cell phone, on a laptop, including the sky viewer. And we're planning to make as much of the education public outreach products as possible available both in Spanish and English. So for citizen science, I highlighted previously the Sloan Digital Sky Survey Galaxies project. That project was so successful, it really launched a whole team of people who run the Zooniverse, zooniverse.org. It's an online citizen science platform that's been very successful. It has citizen science projects available from all different fields, not just astronomy, and we're working with that group to create a pathway so that LSST scientists who have an idea to create a citizen science project can do that and make a subset of the LSST data available for members of the public to help with scientific research. So it's another way to take authentic data out to the public. And here's an example, Space Warps HSC. So this is a version of the Space Warps project using hyper-subprime cam survey data. And a few months ago, this was still running, and when I went a couple days ago to get this screenshot, it's already over. Everything's been classified. And when that happens, you can still go online and classify objects. You'll just get more of the test imagery. So that's really exciting that these projects continue to be of interest to the public. Okay, so I thought it'd be fun to show off some of the nice imagery and photos and highlight some of the recent construction events and milestones with the project. So here you can see this is the mirror coating chamber, and it is on its way to the summit. Oh, and the photo on the edge got kind of cut off, but in the bottom right-hand corner, you can see that there's a very tight fit going through a tunnel. So this is the chamber that will provide the mirror its both reflective and protective coating, and that is done actually at the summit site. And so this is actually half of the coating chamber. It had to be split into two sections in order to be transported. And it was transported initially from France. And so here it is on its way. It's 9 meters in diameter, and it took a lot of logistics planning and a number of different people to make this happen. There were some lights that had to be removed and street signs and cords that were hanging down so nothing would get hung up. Here's an example, or here's a photo of the telescope mount assembly. So this is actually what the camera will be mounted onto. And this is in Spain. So again, just you can get a sense for how big of a project this is, and it takes people all around the world with all different backgrounds and areas of expertise to make this work and happen. So here's a picture of the primary tertiary mirror for LSST in the foreground with a blue protective coating on top, and behind it is the mirror cell. So that's what the mirror will actually sit on when it's at the telescope site. And in this picture, this is at the Richard F. Karras mirror facility in Tucson, Arizona at the University of Arizona. And in this picture, suction cups are being used, so it's a vacuum method to pick up the mirror and put it into its shipping container. And there it is being shipped. So it's on a highway going to a port where it got loaded onto a boat to then go via boat to Chile. So that also gives you a sense of scale. And to close out the talk, before any questions, this is the most recent picture that I could find of the telescope site. So this was taken back in March. And you can see a couple cranes in there if you look closely, and a bunch of cars. And I hope it gives you a sense of the scale and just general excitement for working on a project like this. So if you want, you can follow along with the construction process at lsst.org. You can see some of these images at gallery.lsst.org. You can follow us on Facebook and also Twitter. And thank you for being here tonight. We'll take some questions.
I'm curious, why couldn't they coat the mirror, like in the States, and then transport the mirror up to the summit? Why do they have to coat the mirror to the summit?
Yeah. So yeah, it's a great question. So we. Oh yeah, right. So the question is why do we send the coating chamber to Chile and do the mirror coating at the summit? So the answer is that over time the actual reflective material it essentially wears out and the mirror becomes less reflective than would be optimal. And so approximately every 2 years or so, there's a plan to re-illuminize the mirror. And that will make it significantly higher light collecting power. And if you think about it, even a 10% gain in efficiency is a really big deal in this game. So it makes sense to actually have the coating chamber at the site. There's actually a huge elevator. I think you can. So you see the scaffolding of the dome. That's where the actual telescope will be. And that sort of white vertical structure that's connected to that. There's a giant elevator there that was actually made in Wisconsin. And that is what will take the mirror from its location in the dome down to the coating chamber. And so
they will leave the coating chamber there then?
Yeah, so the coating chamber will stay. So that's what that long white piece that goes out. A lot of the support infrastructure, such as the camera clean room and the coating chamber, that's all located there.
Hey Keith, you could use the laser pointer now because we're not recording the Q&A.
Yeah. So So here's the scaffolding of the dome that's under construction. That big elevator is right here, and then this large area here is where the coating chamber is. The camera clean room is also where all the computers are that are processing this data in real time. Yeah. Yes?
Why was the site in Chile chosen?
So there's a handful of places in the world that are really special from the standpoint of doing ground-based astronomy. The features that we look for are that they have very dark skies. They're very dry in terms of the amount of water vapor in the atmosphere. And we'd like to be as high in altitude as possible so that we're looking through as little of the atmosphere. Because basically, as the light from these distant objects, it's traveled billions of light years to reach us, and then it's only in the last kilometers that it gets all blurred out by the atmosphere. So we try to get up as high as possible. So there's a couple sites in the world that are particularly good. Mauna Kea in Hawaii is outstanding. There's La Palma in Spain, for example. And then in the Andes Mountains of Chile, the Chileans have been very friendly and collaborative over many years. So actually where LSST is sitting, and also actually the Dark Energy Survey is happening on just the next mountain over, so you can see the two at the same time. That's actually, I believe, the first site that was designated specifically as dark skies, like a World Heritage Site specifically for maintaining dark skies, so that everyone can appreciate what the galaxy looks like.
Off the top of your head, Keith, could you give the altitudes for those three places? The one in Spain, the one in Hawaii. So LSST is a little over 2,000 meters elevation. I don't know the figure off the top of my head for Mauna Kea. I think it's quite a bit higher.
13,000 feet.
13,000 feet. Yeah, so that'd be quite a bit higher. And I'm not sure for La Palma. I know that when astronomers go to Hawaii, I haven't personally been yet, but I've been to the site in Chile. But in Hawaii, you actually need to be a bit careful, not to lose your head, because the oxygen is lower, and so you actually typically sleep at a lower elevation. In Chile, the astronomers sleep at the site.
So, question about the black hole that's received, but it touches on reproducibility in your talk, and you guys both did a great job of explaining subjects that are difficult for a lot of us. But the question is, with the black hole, the image, from what I understood, there were 4 different groups that independently worked on the data, and you talk about reproducibility in your, so do you know how consistent, what kind of variability there was between those 4 groups in coming up with the image? Was there quite a bit of difference in it? And then connected to that, I guess the data were collected about 2 years ago, and it took 2 years to come up with this image. Just in general, why 2 years? So, but anyway, first question being, you had 4 groups. How close were each of those groups to that image?
Great, great. Okay, yeah. So the question. Yeah, this image was produced by 4 different groups. How consistent were they? So if you, on the same day that the Event Horizon Telescope made the press release, they also released 5 papers published in astrophysical journals. And so in one of those papers, they actually describe in detail the different methods and the different assumptions that were used by each of the 4 algorithms. My understanding, not personally being a member of the Event Horizon Telescope, is that these teams worked largely independently of each other, and they basically came together on a given day and presented all of their results, not aware of what the other 3 teams were doing, and they basically all came up with the same shape, right? I mean, the exact details might shift a little bit, but you can see they published all 4 analyses in the paper so that you can see exactly how good the agreement was. And I think it's actually really outstanding, and I think a testament to the whole scientific process that they took the care in doing it this way. I'll say that, for example, with the dark energy survey, we actually have multiple redundant methods on almost all the important aspects of our analysis. And we do many of the analyses blinded, in the sense that we deliberately hide aspects of the data from ourselves so that we won't sort of open the envelope until we've decided on all the procedures. And so it's a way of ensuring that even at a subconscious level, that because we've invested so much in collecting this data, we want to be as careful as possible not to let the sort of the human element creep in, even if we're not intending to.
So,
go ahead.
Well, since the observatories in Chile, south of the equator, what percentage of the sky can it survey? Because, I mean, it couldn't be 100%, right? Would you have to have one in the northern hemisphere to get 100%?
That's right, yeah. So the question, how much of the sky can you survey from Chile? So I think this is the image that makes this most clear. So this is shown in equatorial coordinates, so basically projecting the coordinate system of the Earth out into space. So the equator is along the horizon. So Cerro Pachón in Chile is at minus 30 degrees south latitude. So like about here. So you're able to observe the whole southern hemisphere with very good data quality. You can actually go further north, but you're looking through a bit more of the atmosphere. So it's actually, right now, the final observing strategy is still being decided. There's a number of different proposals that are being considered, but I think it's likely that we'll get the whole southern hemisphere as well as significant parts of this equatorial region as well. Yes?
So obviously there's history because you have another telescope in the Astronomical Observatory in Chile, but I was wondering the extent to which, because this is an extraordinarily active earthquake zone because it's right on the boundaries there, what protections, if any, have been made for earthquakes and in that region?
Yeah, that's right. Question about earthquakes and what do we do about it? So earthquakes are just part of life in this region of Chile. It's the telescopes are designed with this in mind. So for LSST, in the documents that the project has adopted for all the engineering specs of the facility, there are particular requirements that are given for the ability to survive earthquakes of different magnitudes. So we can, I can say that with the dark energy survey, for example, that's been running now for several years, there have been instances where people have felt tremors there, and even instances where the telescope had to go offline, and it took a couple days to get all the optics back in alignment. But we've been fortunate not to have a major incident, and the observatories are built to be as robust as reasonably possible.
I'll chime in to say that also the data facility, the data processing facility that we're building in Chile also has earthquake. It's also earthquake. What is the word? Resistant. Yeah, earthquake resistant, not proof, but all of the engineering that's needed so that it can withstand an earthquake is in place, so that the data facility, even off of the summit site, will remain intact. And at that, it's, I believe, state of the art for Chile right now.
There's multiple copies of the data so that we are hopefully emergency proof.
Yeah, I was thinking in terms of shaking, you have a lot of mass there, a lot of inertia that would be affected by an earthquake there. Just whether it easily break, the damage would be substantial in certain cases.
Yeah, it's definitely part of the design of the facility, but it's not. It's not my particular area of interest. You'd have to ask the engineers for all the details. Yes?
My question is kind of a follow-on to the previous question, and that is, how do you keep the telescope focused on one sliver of sky for, I guess, 15 seconds? You try to take a picture so that it's as clear as possible, and then to move the telescope even just slightly to the next rectangle of sky you want to image. What's the technology you guys use to keep all that mass stable and then account for the rotations of the Earth and whatever else you got to figure out? How's it done?
Right. So excellent question. So the question is, how do we do the guiding and the tracking during these long exposures? 15 seconds for LSST is quite long. However, with the dark energy survey now, we're actually doing 90-second exposures, so even longer, and we often go as long as 5 minutes when we're taking deep images of a supernova field. So the way this typically works is that on the entire focal plane of the camera, most of the sensors are dedicated for the science image and are read out at the end of each of the 15-second exposures. However, there are particular sensors that are, in the case of LSST, they're located at these corner positions. And what they're doing is actually collecting data and digitizing it throughout the exposure. So there are sets of sensors that are designed for actually honing on to bright stars and basically tracking their position during the exposure. And there's positioning basically for the whole camera, right, to make adjustments if need be during the exposure. In addition, there's also sensors that are designed, they're actually placed slightly in and out of focus so that you can not only adjust the position, but also the focus of the camera. One of the aspects of LSST that's really challenging is because of the optical design, the light is actually coming in at a higher incidence angle than is usual. And so there's extremely tight tolerances on the actual positioning of the sensors on the focal plane to make sure that you're actually getting the sharpest image. And so all of this can be adjusted. And in fact, those, I think you can see it on the image that Ellen showed here. I'll zoom ahead real quick. Yeah, I think this is the best spot to see it. So this is the mirror cell that holds that primary tertiary mirror. It's a single piece of glass, but it's actually been curved to two different shapes because the light will take 3 bounces before it goes to the camera. But that mirror sits on the cell, and all these little components that you see here are actuators that can dynamically adjust the shape of the mirror to respond to changes in temperature, changes in the gravitational forces as we're observing different parts of the sky. So it's all a system that can be adjusted in real time to actually produce the very best image quality. In the very back.
You alluded to this earlier, the changing dynamics of the science team that you're working at with the shared data. Could you allude on that? As how has it changed your working with other physicists and with your null hypothesis and having the different groups that you talked about earlier?
Right. So I would say that, at least for me personally, I've spent almost all of my scientific career working on large surveys such as this. I would say that it's becoming more and more of a trend in modern astrophysics research to, when you write a paper, you often have several hundred co-authors, right? And the reality is that these experiments are so technically and scientifically challenging that it would be almost impossible for any one person or even one, say, university group to do it on their own. I would say one of the patterns that's appearing is that because all the data are public, there's more and more opportunity to not just analyze the data with your own instrument, like with your own experiment that you're sort of directly contributing to, but also accessing data from other facilities that have mapped the same part of the sky, but for example, with a different technique or in a different wavelength. And so more and more we're finding that we get the most robust results by actually combining many different ways of looking at the universe and actually accessing the data from multiple different surveys. I'd say one of my postdocs here, who's in the audience, Ross Cawthon, is actually an expert on doing this with optical surveys in the cosmic microwave background. So I'd say more and more we are finding that the really interesting science that can be done is actually at these interfaces between different experiments. But it means that I'm typically on several different telecons every day with collaborators in many different time zones. I've been to now 6 different continents for scientific research, including Antarctica. It's just the nature of our field that we look at things very much from a global perspective. Yeah, over here.
Here.
In the white shirt. Yeah, we'll get you next.
You said you're going to gather data over a 10-year period.
That's right.
Will you get information regarding the expansion of the galaxies, universe during that time? Is it possible to calculate the expansion rate? And also, do you suspect, you said 95% is energy matter. Will that be persistent for all the galaxies? Same 95%?
Good. Let me tackle the first question, which is can we see the expansion of the universe during the 10 years of LSST operations? Is that correct?
Yes.
Yeah. So the universe is constantly changing, but it's changing on a time scale of billions of years that often isn't always perceptible to humans. There's these special events like a star explodes as a supernova. But most often, the universe is changing on this very gradual time scale. That being said, these galaxies are moving away from us at, even the closest ones at hundreds of kilometers per second. But the distances are so large that that's actually quite difficult to measure. So in the 10 years of LSST, it would be extremely difficult to measure the expansion of the universe during those 10 years itself. The way that we think about this is that because light travels at a finite speed, light travels 186,000 miles per second or 300,000 kilometers per second, that as we look at objects that are further away, we're also looking back in time. So in a single, let me go back up. Let me go back up here. Right? So what that means is that we're seeing this asteroid as it was minutes ago. We're seeing the star as it was thousands of years ago. We're seeing these galaxies as they were millions of years ago, and these galaxies as they were billions of years ago. So we don't see the universe changing directly, but what we see is all these different snapshots of what the universe was doing at different periods in its history. It'd be a little bit like if say, aliens came and visited Earth for just one day, and they were able to look at the entire human species, but they couldn't watch a baby grow into an adult, right? But by seeing humans at all different stages, humans learning to talk and learning to walk and learning to drive and going to college and so forth, they might infer, right, that all of these different people is actually one species, just at different stages in ort life. And so that's kind of the way that we think about the universe, is that we see all these individual snapshots, and we have to use our sort of our creativity and intelligence in our modeling to try to stitch these together and make a coherent picture. So that's the first part. The second part, could you remind me again?
That's the part where you said 95%.
Yes.
The estimate is dark matter. Is that true for all galaxies? And are there any theoretical predictions for all the experiments you are doing, so that maybe at the end of every month we can compare a theory for our Milky Way, then expand it, and probably modify the theory that is being predicted by astronomers and all that, and come up with a better theory? Is there any kind of a feedback loop during your 10-year period, or you wait at the end of 10 years, collect data, and then make a prediction? Or?
Sure. So this 95% figure, that is a statement about the universe at large as it is today. It turns out that the relative fractions of dark matter and of dark energy, they're actually changing with time. The amazing thing about dark energy, the part that's so surprising, is that its density appears to be uniform. And if you think about that, imagine that the scale factor of the universe were to grow by a factor of 2, such that the volume is 8 times larger. Now, the average mass density would drop by a factor of 8, right? It's imagine if you had a box, you make it twice as big, so 8 times the volume, and you have the same number of particles inside, and so the density drops by a factor of 8. Now, the crazy thing about dark energy is that its density is constant, right? So now you just have 8 times as much dark energy, okay? It's this very weird substance that we don't have any kind of explanation for it, or why the universe behaves quite this way. The particular density is a very perplexing number that doesn't really match up with some of our other predictions from particle physics. It's a big mystery, and it's something that's been changing throughout the history of the universe. As the universe continues to age, dark energy will become more and more important. The galaxies will accelerate away from each other faster and faster, and eventually we'll get to a point where we look out in the night sky and it just looks dark because the neighboring galaxies are so far away. Right? It's a kind of a strange way to think about the universe ending, but based on our current data, that's how it looks like it'll be. Fortunately, this is billions of years from now. So don't sell off all your property. Yeah, find another universe, right? So I'd say one of the main science drivers for LSST, and in fact many other surveys that are happening in the next decade, is precisely to try to understand this dark energy and the dark matter. The dark matter is yet again like another substance. Its density is varying throughout the universe. There's way more that we could talk about, but I guess I want to leave some time for other questions too. Yes?
Did you say that there was some kind of a limiting factor on how far into the universe, or like there's an edge to the universe, not so much a physical edge, but like a limit? There's some sort of a limiting factor on how far back, if you will, we can see it. Can you see as far as there is something to see?
That's, yeah. So question, how far can we see and what's the limit?
Yeah.
Right. So this is somehow the answer, actually. So as you look at objects that are far away, you're looking back in time. Okay? And so this is actually the very most distant light that we can see. It's light that was emitted from the heat of the Big Bang itself. The universe was cooling down, and basically these photons were emitted when the universe finally cooled down enough that neutral atoms could form, and light could propagate freely throughout the universe. So this is light that's traveled now for about 13.7 billion years. And this is, like, if you were, like, you can't really look back further than this because the photons just haven't reached us.
So there could be more.
Yeah, so there's no reason for us to think that there's like an edge, like an actual physical edge of the universe. It's just a horizon in the sense of the furthest that we could see. So if there were, astronomers on Earth a billion years from now, or like dinosaur astronomers, for example, they would see different amounts of the universe just because of the amount of time that light has had to travel, if that makes sense. But the way I think about it is, like, imagine you're on like the middle of the Pacific Ocean and all you see is ocean all around you, right? It doesn't look, looks the same in all directions. There's no reason to think that the ocean doesn't keep on going for a very, very long way. And that's how we think the universe is. Yep.
I know the EHT isn't your turf, but one of the things that struck me about that image and the description of it in the popular press was that it was supposed to be a perfectly circular thing in the middle of that image. And yet the image itself looks pretty asymmetric. What causes that asymmetry, or why does the image appear that way as opposed to appearing like a perfect donut with the same luminance all the way around?
Yeah, right. Question: Why does it have this shape?
Partly the shape, but
also the asymmetry. Right. So again, I am not an expert on the Event Horizon Telescope, but my best understanding of what is happening is that almost all black holes are expected to have an angular momentum that's associated with them. In other words, they're spinning. And so that means that they themselves are spinning, and also the material that's falling in towards the black hole forms into an accretion disk. And so that material, as it's swirling in, that's actually producing the light that we see. And so the effect that's causing the asymmetry is basically you have this whole rotating system, and in particular, when a black hole is rotating, it actually distorts the space-time around it in a rotational way. This effect has been measured on the Earth. There was a dedicated NASA space probe to measure this called Gravity Probe B. And so we really do find that the equations of general relativity, predicted by Einstein and company, that spinning masses actually drag the space-time around them. And so what we're seeing here is basically that rotational imprint in space-time actually distorting the light that we're seeing from the accretion disk of this black hole. So people who study rotating black holes were extremely excited to see this image, right? Because it's basically fully consistent with what you would have predicted from general relativity. It's yet another passing with flying colors for the theory. Yep.
Is the 10-year lifespan a hard limit, or if you get more money, it might continue?
That's the design based on the operations funding that was that's expected. It's possible to continue. It may also be that after 10 years, we've collected so much data that you're kind of at the point of diminishing returns, and maybe it's time to either build. That's the crazy thing about science, right? We're always kind of pushing back the frontier. And so what was yesterday's discovery is now in the textbooks. And so we expect that 10 years from now, it's possible that the scientific questions that we're asking will be different. But there's no reason to, everything about LSST has been designed for sustainability and to last. So I see no reason why, if there wasn't additional support, that you couldn't operate it for longer.
So a question for Ellen. I thought the dome was a really cool idea for like the alert stream, and I don't know how developed it is at this point, but I'm just wondering like what it would look like with 10 million alerts every night.
Oh,
like how realistic it's going to
yeah. Good question. So I think.
Can you repeat the question, please?
Oh yes. So the question is for the education and public outreach effort to have the LSST alert stream in a full dome format for planetariums. What would it look like to have 10 million alerts? And we will curate them and take some out. I don't think we can have 10 million alerts. That's a good point, good question, and I should clarify next time that it will be just a subset of the alerts. That's it's an interesting question though, because we've talked a lot about what we can do from an education and outreach perspective with the alert stream, because it's both really exciting, it's immediately tangible in some ways, and it's overwhelming all in the same moment. And so that's what we've come up with so far. And I also am really curious to see what it will look like. So we're building the different education outreach components in a staggered way. So right now we're focusing on building everything for formal education classrooms, and then we're going to tackle each of the next components over the next several years until LSST operations. Thank you.
Can I follow up on the education aspect? Can you go back to that photo that you've shown a couple of times with the asteroid, the local star, the millions year away, nearby this one? I've never seen this before, and probably second to Earthrise. This is a pretty amazing idea graphically, in that this is a time tunnel. You're looking at light seconds, light years, millions of light years, and billions of light years. Is there a way to make that into like a dorm poster? Thinking, Pink Floyd only.
Yeah. So I mean, it's interesting, right? When you think about the opportunities that the education public outreach team has, I think what LSST is really good at in terms of what the project can do is making these digital experiences and these digital resources available. However, the scientists can also sort of use that as a jumping off point and try to do things at their own institutions, or try to have more face-to-face contact. I think in reality you need both, and I think that there's really with something like LSST, I think it's hard to say exactly whether it's it'll become sort of a household name like Hubble and everyone will know it. I don't know, maybe we need to put it on milk cartons or put it on the posters at the bus stations. I think we should be really creative and like open to thinking about how we can advertise that. I don't know if you have more to say about that, Ellen.
Yeah, I guess there's so many things that you can do, right, with LSST from an education and public outreach perspective. And so creating posters and putting this in the classroom in some way is a great idea. And we've had so many great ideas from all over the world coming into us. And I think what the LSST education from like the project standpoint has decided to focus on is actually making parts of the data accessible and available to the public, right? So using authentic LSST data and making it available in the classroom or through citizen science projects, through the Sky Viewer, right, and through the Multimedia Gallery.
So is this a standard type of slide that lots of people use in talks like this, or is this something that you came up with?
Oh, so so we have this informal messaging service that we use in the Dark Energy Survey, Slack. Maybe some of you use it. And so people are always just sort of chattering about various things. And one of the channels that is very popular is just called Beautiful Images, right? It's literally people just find beautiful images of the night sky and just post them, right? Just our own data. They find a particularly beautiful galaxy or a cluster of galaxies, or one time we accidentally imaged a comet, and it was so big and bright that it filled the entire field of view. And so sometimes people will just post images that they just like. And so someone just posted this on that channel one day. They just said, hey, look, here's an image. And when you look at this carefully, you see that there's just this enormous range of physical scales that's all represented in a field of view that's just a few arc minutes across.
And that's the context that I wouldn't have gotten if you hadn't had that labeled like that. I mean, that is a time tunnel, not like anything I've ever seen before, and I hope you can milk that cow.
Yeah. It's like looking down the Grand Canyon or something, but on an even bigger scale.
Yeah.
Yeah.
Thank you. Yeah, that's great.
Yeah. Yep.
This is just one last question, because it bugs me that, so the idea is you're going to map enough of the sky to be able to do a lot of science. It's not really, you're concerned about mapping 100% of the sky, right? Because obviously the north is going to be mapped, but you're getting a big enough sample to do all the science that you need to do.
Yeah, so that's what so the question is like, you can still do science, right, with some fraction of the sky.
Right.
And so that's what I meant by saying that the particular universe that we live in is this statistical realization, right? Our models of physics, they don't tell us where a particular galaxy will be, or what particular the star Betelgeuse will have so many planets, right? I mean, it doesn't tell us like specifically what will happen. What it tells us is distributions, correlations, patterns that we can look for. And so you could look at this image, for example, and you could ask, well, how much of this image would you need in order to figure out the pattern?
Right. I see.
Right? Similarly, if you were to look at, at this image, how much of this image would you need to figure out the pattern? Right? The more of the sky that we can see, the more precisely we can learn about the laws of nature, but we can still make a significant amount of headway without seeing literally all the 2 trillion galaxies in the universe.
Right.
Yeah. Yep.
I was curious about how the education outreach was structured. Is it centered somewhere, or is it just a collaboration with how many institutions? Or
yeah, that's
it's the same funding as the LSST.
Yeah, that's a great question. So the question is, how is the education public outreach structured? And so we are funded by the same funding as LSST construction, specifically the NSF and international partners. And there's a team of people based in Tucson, Arizona, and that's the project headquarters. And so that's where the education public outreach team is, save for myself. And I work part-time from here. And then our Chilean outreach specialist, who's in Chile. And within the education public outreach team, people focus on different areas. So some people focus on the formal education front. Some people are more focused and specific to the planetarium and multimedia side of things. But we're a team of maybe 10 people now. And there's this other untapped, yet to be tapped education and outreach team, which is actual, like the LSST scientists, right? And that there's thousands of scientists who will be using LSST data and who will also be interested, I hope, a subset of them, in doing education public outreach work and running events or activities and making available some of what we've done in their hometown. So that will happen, that part of the education outreach team will happen during LSST operations.
Yeah. At least what we have found with the education public outreach and the dark energy survey is that some of the initiatives that have been most successful are those that really tapped into the individual interests and hobbies of the scientists, right? So like this image. So I should say that weak lensing mass map was made by the same person who produced this cartoon. Literally the same person, Shi-Wei Chang, who's our personal friend. We knew her in grad school, right? She made both this breakthrough scientific image and also made this cartoon, right? And in many ways, these education and outreach opportunities that have been kind of at the interface of popular culture and art and kind of tapped into the individual interests of the scientists have been the ones that have also been the most interest to the public as well. So maybe that's not a surprise, right? That if you want to reach the broadest audience, you should try, speaking not only the language of mathematics and science, but also speaking languages that, connect with more people.
I'll add briefly that in terms of structure, LSST is kind of unique in that education public outreach is a dedicated subsystem of the project, which means there are several subsystems like data management, telescope and site, camera, right? These are all teams building what is going to be the LSST survey. And LSST is one of the first, if not the first, that has a dedicated subsystem or group of people to work on education and public outreach. So we're at all of the big reviews of the project. We have our own requirements documents, and that's really unique among ground-based telescopes.
A couple more?
Going back to the weak gravitational lensing picture, for me, it's just I'm looking at a picture, but you're looking at it and looking at that picture, what does it actually tell you as a professional when you're looking at that picture, or does it have a scientific, can you see something there I can't?
Yeah, that's right. I guess it's maybe like a Rorschach test, right? So what we do in practice is that these the color scale here is again representing differences in the mass measured along the line of sight. And the way that you actually construct this image is that there's literally millions and millions of galaxies that we've surveyed. And as the light from those distant galaxies is passing by the foreground mass distribution, the shapes of those galaxies are very slightly distorted, and they're distorted in a way that's coherent. So that even though the galaxies intrinsically all have more or less random orientations, the fact that that the light from all those galaxies is passing by the same intervening mass induces a very slight correlation. It's an extremely small effect, and so you need to measure this with literally hundreds or thousands of galaxies to even be able to sense it. Once we've sensed it, though, once we've looked at the correlated shapes of the galaxies, we can infer the regions of the universe that are more or less dense than others, and that's what this color scale actually represents. And then what we do is that we actually look at sort of the patterns of these shapes in the galaxies at different angular scales. And again, it's a statistical measurement, right? We're not predicting the shapes of individual galaxies. What we're really looking for is patterns in different angular scales of how these shapes are correlated. It's a little bit difficult to explain without going pretty heavy into the mathematics. But what this is, it's actually one of the very most sensitive tests that we have of dark matter and dark energy, because these patterns of correlations in the shapes of the galaxies, they are sensitive not only to the amount of mass in the universe and how it's distributed, but also the particular angles on the sky. The angles that we measure actually depend on the expansion history of the universe. That because the universe has actually been growing at an accelerating rate, sort of the angle, the angles and the distances that you would think about measuring in a normal sort of three-dimensional flat universe that's not expanding, those shapes actually get projected onto different angles on the sky when we look into the distant universe. And so all of these effects are come together when we make the measurement. So we're learning about the expansion history of the universe. We're learning about how structures in the universe have grown over time. It allows us to understand the dark matter, the dark energy, test the laws of gravity on size scales that are totally different from the Earth. It's really one of the very most powerful tests that we have. But because it's kind of abstract and it's not something that you can see, like as a human, you can't look at one of these images and be able to see this effect. It's something that you can only measure statistically through advanced computer algorithms and so forth. It's something that's more difficult to talk about with the public, but it's really one of the most important techniques that we use in modern cosmology.
Follow-up, if you're going to show that image to a classroom, what's the teacher going to say about this? I mean,
I'm gonna send that one to Ellen.
Block that punch.
Sure.
We're not showing that to the classroom. Just to be clear, we're showing different types of imagery. Yeah, this is not something that we're going to show to a classroom.
It's a good question, though. I mean, it's interesting to sort of, I mean, we want to be as authentic as possible in terms of really talking about what we do in the details. At the same time, I guess we want to be careful not to overwhelm and confuse.
Yeah, so that's something we've given a lot of thought to on the EPO team, right? Is what is LSST really good at? What are people teaching in the classroom? And where's the sweet spot, right? Where we can take what LSST does and hopefully it will be engaging and interesting and match really well what's being taught in the classroom.
I think there was one more question, or are we done?
Well, I just had a quick question. Is it the CCDs, that's the device that captures the actual image? Is that correct?
That's right.
So I'm assuming that technology continues to improve. Are the CCDs of this facility interchangeable? So 5 years from now, if they've dramatically improved the capacity of CCDs, are you able to take out the ones that were installed today and put in new ones, or is it too expensive to do that, or is the improvement not is it flattening out now, or?
Right. Okay. So yeah. So the question about the future of the CCDs and will we ever seek to replace the instrument? In what considerations? So there's a question earlier about what do you do after 10 years of LSST, right? And I think that upgrading the instrument, the instrumentation on the focal plane, is one of the options that would be available. It's actually quite common for telescopes to get a new instrument, and in fact that's exactly what happened with the Dark Energy Survey. It's actually a 50-year-old telescope, but it got this new instrument, the Dark Energy Camera, a 500 megapixel camera, and it gave totally new life to the facility, right? It's now one of the most popular and most used observatories in astronomy, with many thousands of users. So taking an old telescope and giving it a new instrument with improved sensors, right? I mean, that can be a very efficient and economical way of kind of keeping the science moving. I think in the case of LSST specifically, we're still at the point where we're constructing it, and people are beginning to think about what other instrumentation options you could pursue. But at this point, we're really focusing on trying to get it finished on time and under budget. And that is enough to keep all of us more than busy. So.
All right, thank you very much.